Can you see my laser pointer here?
Yes.
Okay, cool. I can also use pen, maybe. Yeah.
Yep, that's all good. Okay, perfect. So, Mojtaba, it's all yours.
Yeah. So today I want to actually start with to present a paper called DeepMatch, based on the balancing deep covariate representation for causal inference using adversarial training by Nathan Kalos, and it was published. This paper was published in ICML 2020. And my name is Mojtaba Valipour, and I'm a Ph.D. student of computer science at Data Analytical Lab. So I will follow a very general outline, I can say. First, I'm gonna give you, let's start with the problem and maybe even the motivation behind the problem and why they want to solve this kind of problem. And then I will discuss how they just tackle this kind of problem, and then we will see some experiment. And lastly, we will also conclude with some sort of takeaways. Yeah. So for the problem, what's the motivation behind this problem? What's the problem and what's the motivation? I'm pretty sure that you know already what's the Simpson paradox, but let's recap very, in a very fast way. So let's say that we have a new disease called COVID-20. And for this COVID-20, it was, we just found two kind of treatment, okay? The first one is the red pill, and the second one is the blue pill that you have to take. Let's call this, this variable as treatment. And we have also another variable, let's call it X, but shows the condition of the individual characteristics, okay? So if the patient has a mild situation, we will have the condition as equal to 0. And if he or she has a severe condition, it will be X is equal to 1. And we also have a outcome Y, which actually shows that if the patient end up to be alive or dead. So let's see an example to see how this, this can be sometimes if we don't consider really a very randomized assignment, treatment assignment, then how we can face some kind of problems. Okay. This is a very general problem in causal inference. So let's say that we have this causal graph. Okay, the treatment is the cause of the outcome, and therefore we are interested to calculate the conditional distribution of the outcome. And as you can see here, the distribution of the population in our case, in this example, is that okay, the number of people that were treated by the red pill were around 1,500, but the number of people that were treated by the blue pill was around 550. So much less than those guys that were treated by the red pill. So it's not really balanced. As you can see here, 240 of those that were treated by the red pill were dead, and for the blue pill, it was only 105. So the mortality rate of the red pill is around 16%, and the mortality rate of the blue pill is around 19%. As you can see here, if you just check this table, you can say that okay, because the red pill has the less mortality rate, so maybe it's a better treatment for this kind of disease. But if you just let's say that in our causal graph we have also another variable that's going. When this is the case, we are going to, if we just see the same distribution, but by with the different treatment groups. If we categorize the whole population with different treatment groups, then this is going to be we can conclude a different conclusion. Okay, so let's see that again, the same table. Okay, the same data. As you can see here in the mild case, the number of people that were treated by the red pill was around 1,400 people, and this is much more than those people that were treated for the severe condition. Okay, and which it was around 100%. So as you can see here, the severe condition and the mild condition has a very different distribution. And also, you can see that the number of people that has a mild condition uh, and were treated by the red pill is much more than those guys that were treated by the blue pill. So if you just consider the mild case, you will see that the number of people that you have in your data set is much more than for the first treatment comparing to the second one. So here, if you just consider the mild case, maybe if we just want to using this data set, nothing else, we cannot use another kind of, let's say more information or something, then um, we can conclude that, okay, still the blue pill has the less mortality rate, which is only 10%, if we just ignore the number of people. But you can conclude that, okay, uh, is that the case? Is that the only thing that we can conclude? Okay, blue pill is no better, but not necessarily. That's not the case. It's really depends to the cause of death. And also, let's say that maybe if the number of blue pill, number of persons that were treated by the blue pill is so much less than the red pill ones, maybe the blue pill is a much scarce, much more scarce treatment, and it's much more valuable. So, they were only, they were just that the doctors just used that blue pill only for people that had the severe condition. But this kind of problem actually raised from the fact that if we just use, see that, okay, how we just calculate that 16% as the total mortality rate for the red pill, we will see that the weight that were multiplied by each of these mild and severe condition is absolutely different, and for the mild one is much more effective than the severe one. So this kind of unbalanced weight is the main motivation for this paper, to come up with, with some sort of algorithm that is going to balance this kind of, you know, condition, let's say, and we are going to hopefully end up with a better experiment. So, but there is one more problem. Let's say that you know, usually in realistic world, we don't have necessarily access to those confounders. Okay, those are almost always, unobserved confounders for us. So in those cases, let's say that we have also have access to any kind of high dimensional data, which are really rich. For example, in this example that I just brought up, let's say that we have access to electronic health records or even medical imaging, which is going to, you know, let's say that if we had access to this high dimensional data, maybe hopefully they have all the information which is necessary for us to, to tackle those unobserved confounder. Okay, so we can, if we just use, if we somehow find some representation, a very good and rich representation of from those rich high dimensional data, maybe we can justify the assumption of no unobserved confounders, and therefore we can well model those kind of things by neural network. But still there is one more problem. Usually a standard method that we already have here, like for example propensity score and all the other methods that are linear, they are really fragile, and if we just had neural network, it's going to be much more worse. It's not really, cool. So in this paper, they just propose a method based on adversarial training to find just some weights that make control and treatment population are somehow identical. So the distribution should be identical in the end by any neural network classifier. So there is a game between two kind of very similar to the whole idea of adversarial training. And there is a min-max game here, and you will see much more detail in further slide. But let's see why this actually works, why they are, they want to somehow find some weights that are actually is going to make the two different population, treatment and control group, indistinguishable. I'm pretty sure that you're familiar with the definition of the treatment group and the control group, but let's recap fast. The treatment group is any group that received the treatment, and the control group is all the other groups that actually they might receive, for example, another treatment or not any kind of treatment or anything else, any kind of counterfactual, I can say. So let's see this example. Okay, let's say that we have two group, okay, a control group and a treatment group. Control group was shown as red here that you can see, and the treatment group was shown as for different, individual. They were, uh, let's say that we have many units here, and all these units uh, were, assigned by some sort of treatment, okay, to treatment group or control group. This chart just showed that two baseline confounders. So we have a baseline confounder here and another one here. So this is another example than the previous one. Just focus on this one. So if we want to somehow train a discriminator that discriminate between this blue group, the treatment group, and the control group, we can easily train a model. Okay. And as you can see here, we just fit a linear model that can separate actually the blue one and the treatment group and the control group. But let's rebate the control group and let's try to fool that discriminator. If that's the case, if we did that, maybe we can end up with another discriminator, which in the end is going to again discriminate between the treatment group and the control group. And if we continue this procedure, we will see that we can, rebate, we can train another discriminator, and we can do that continuously until we can actually find some sort of weight that is going to fool all kind of discriminators equally. Okay, and this is our goal in this paper. So let's see if we just formalize the problem. Okay, what we want to achieve. So let's say that we have, some confounders that are covariates in our case. These are pre-treatment covariates that used to characterize the individuals. Let's say that we have also a treatment variable which shows that if if that case, if that group, if that individual received that specific treatment or not. And we also have some outcome, but these outcome are not necessarily observed. These are potential outcomes. But we also have some observed outcome, of course. For example, for the treatment, we might know that this guy were dead or he was alive in the end. And data is, of course, NIAD observation of X, T, and Y of observation. We are interested to calculate the average treatment effect on the treated one. So it's going to be equal to, this tau is equal to expectation of the treatment, the outcome of the treatment, the difference of the outcome of the treatment and the untreated ones. Okay. So we are interested to find this problem, but the problem still is untrivial because we have observation for the treated ones. For those treated cases, we know that the outcome of the treated ones, but not necessarily we are aware of the untreated cases. And this is this is one problem that we might need to somehow handle, and this is because of the counterfactual. So they just assume that the ignorability assumption is valid here. So what does that mean? It means that the untreated outcome is actually independent of the treatment assignment given the confounders. Okay, given the covariates, you can assume that this untreated outcome is absolutely independent of the treatment assignment. So let's go further and maybe simplify this problem a bit. Let's say that we just given some weights and we can absolutely approximate that average treatment effect on the treated with this equalization. As you can see here, it is just that the right hand side is just weighted sum of the you just multiply some weights over all the observation sample that you had, and you are going to find the difference. And absolutely, you just assume that in this, according to this formula, you just assume that for the treatment units, the weight is equal to 1, and you're going to find the control weights. So let's go further and see that, okay, can we somehow, for example, let's say that alongside weights, we also somehow, some people just gave us an estimator of mu naught, okay, which mu naught is actually the probability of not treated given the covariates, okay, as you can see here. So this is the mu naught. So I'm interested actually to also, use this kind of information as a priori. And as you can see here, the new approximation can be written by this formula, but you can, it is just a very simple centralization formula. It is just this, that you just centralize that with the approximation of mu naught. A very common way to actually solve this kind of problem is called inverse probability weighting, which use propensity score. What's propensity score? To just remind you, it is actually the probability, the conditional probability of treatment. Okay, and as you can see here, the IPW weights is going to be equal to the propensity score divided by the 1 minus propensity score. But unfortunately, this approach is really highly unstable. And let's assume that if we just replace this propensity score with a neural network, it's going to just make the problem worse. So what they did to solve, to how they tackle this kind of problems. So instead they just use another formula, they just find out that, okay, in another paper, actually the same author shows that actually the error of the approximation of the treatment is, it can be decomposed to two a statement, but this two is going to base on the variance and the mu naught, okay, and the variance is equal to this one. And we are interested absolutely to find uh, the worst, the worst case error of the whole problem, the whole weight assignments. But what is this IPM here that you can see in this formula? So this is nothing. This is the IPM of two different kind of let's say weighting for positive and the negative ones for the control and the treatment one, and it was also regularized with some regularization technique here. And the IPM is, this is a very famous formula actually in this topic, and they just shows that, okay, this is, we can actually calculate the same thing with this kind of information. And as you can see here, IPM of two weighted set, let's say that this one and this one is equal to the supremum of the the weighted sum of the positive one minus the difference between the positive weighted sum of positive one minus the negative ones. And this is a very general formula in this part of the research. So, but still there is some problem with this IPM. Okay, this is not their paper, let's say that proposal. They just shows that, okay, this is the standard approach, and this standard approach has some problem. So what kind of problem? For example, the first one is that IPM is not a closed form. And also, if you just want to use directly alternative saddle point finding methods, it's going to be problematic, and you cannot optimize the problem very well. So instead of this IPM, they just propose another discriminativity method, discriminativity distance. They call it DD, and we will see that how they just propose this position in this part of my slides. So let's say that you have a classification task between the positive samples and the negative samples with weighted data. Okay, this is our classification. That's what we are interested to find out. And we just define a logistic loss of the discriminator score. And this logistic loss is as easy as this one, and it's just a weighted sum of some loss function, okay, for those weighted values. And if we just open this loss function, if we just see that what is this, this L small, we will see that it is, they the author proposed to use this log2 minus log1 plus e minus, e to the power of minus b. But where that comes from? Okay, if we just add log1 minus log1 to the whole sentence, we will see that actually this is equal to log1 minus log1 plus e to the power of minus b minus log1 minus log2, which is equal to this statement. And as you can see here, this is just the the a centralized version of, we just centered this value and you just take it a log. And this is just the probability of the being treated given the conditional probability of being treated. So know you're familiar with this. Let's go and see how we can actually, why this discriminativity score is going to somehow help us. So they just define the discriminativity distance given any, let's say, class function f and psi greater than 0. We can define this discriminativity distance as follows. So it is just the infimum of all these losses that you can see here, which it was regularized by some value called loss psi. So they shows that as just to just show you, before we just discussed the theoretical guarantees that they just provide, that they just shows that, okay, experimentally, that this discriminative distance is somehow equal to the IPM. Okay, so if you just scale the DD distance that they just proposed with the IPM, and if you just scale that one, so the blue one is the DD distance, but if you just scale that with something, which you can see as the orange ones, you can see that it's going to, if you just increase the this regularization error, then it's going to converge to the actually the IPM that we are interested in. And they also showed some sort of other experiment for this part. We just can ignore this one. Okay, let's see and how DD is, how DD and IPM are comparable. Okay, so they just propose actually some theorems. The first one is that they just shows that the DD actually is fine. The DD squared is fine at non-negative. So actually, the root square of DD squared is well defined. And they also shows that if the IPM is, if two weights are balanced, then the IPM is going to be 0. Okay. They also show that the DD is going to be also 0. And they also this is the the both way relationship between DD and IPM. They also shows that for those imbalanced weights, are they also equal somehow, or are they is there any relationship between these two? So they just shows that the ratio between IPM and DD actually is bounded between very interesting value. And they also shows that if you just increase the the size, going to, as you just see in the previous slide, if you just increase the regularization, it's going to, in the end, the scaled version of DD is going to converge to the IP. So how they just optimize this problem? Okay, let's say that we know have a discriminative distance, we know have a DD distance, it's going to be fine, but let's find the optimization problem. So they just define the optimization as the arg mean of this I squared of W plus again another regularization, but we are interested in that I squared. This I squared is absolutely the DD distance. Okay. And they also prove that this problem is converse for any class function f and psi and lambda positive. And they just discussed that later, that if given an oracle, this is solvable using conditional gradient, which is Frank-Wolf. But still there is some sort of problem that they might tackle, because if you have a very complex variables or relationship in your data set, let's say that very high reach dimensional data, then you have to absolutely consider a neural network discriminator F. Okay, so far you have W, and W is a neural network, no, you also want to consider a neural network for F, okay? And this F, unfortunately, if you want to just use the conditional gradient method, it's not going to be easy anymore, okay? And absolutely, it's going to need longer optimization for dense weights, and it's also very hard to fully optimize discriminator for Oracle steps. So in the next part in the paper, they just Lagrangified weight normalization. They parameterize W as a network and also choose appropriate activation. This is very common, in all the deep neural network design. And they also shows that how we can actually have the min max, uh, you know, activate min max optimization problem, and how we can play actually a zero sum game to just alternate the optend very similar to the GAN, and how we can achieve the same goal. They also shows that this, the approximation with these new weights is going to be, it's going to end up to converge in the end to the true, average treatment effect that we are interested in. So they also, show some different result on different tasks. Uh, my guess is that it's not honestly enough. It's good, but it's not that enough. Okay, so let's see what kind of experiment they just run. As you can see here, there is 3 different table. They just put that into one. There is many different method here that you can see. These are all old methods. This is just propensity score. This is the same IPW that we just the inverted probability weight that we just discussed. This is the regression methods. These are some other methods called doubly revasted methods, and all of these together are going to be compared with the DeepMatch method that they just proposed. Okay, and this zero and this half that you can see here is just the psi regularization that you just saw. As you can see here, the first experiment was actually just a fully connected, and this fully connected was was tested on a very synthetic data set. The second was they had a image data set, and so they just used the convolutional neural network instead of the fully connected. And as the third test, actually they used the realistic data called clinical twins, of course, with the convolutional neural network. As you can see here in the synthetic version, actually the performance is really well comparing to the old methods. That's somehow very interesting. But not necessarily always. For example, in convolutional, I really can see a big difference here, and also for the realistic one, it's still good. So to just summary the whole paper, they just actually propose a method to training the balancing weights, okay? And we just going to learn those balancing weights against another adversarial discriminator. And they just show theoretical guarantees and also some empirical results to support deep math, which yield stable balancing weights. And they also actually improved the causal estimation, even when there was actually an appropriate representation, even when there wasn't any appropriate representation. And this is the coolest part of this paper. But all the papers, maybe that they had some cool advantages. They also had, they are going to introduce some burden, let's say. So for this paper, that's because of the limitation is the heavy computational burden of searching over the Lagrange multiplier. Okay, in the weight normalization part, they just use a methodology that is not really computationally efficient. So the thing that I really like to see in this, I thought that it might be interesting if they added this kind of a stuff. Is going to be more realistic experiment. Maybe just can elaborate the effectiveness for me, for us, and it was also interesting if just if they just somehow compare maybe to more recent works such as for example, let's say Kazakh, because Kazakh is actually based on the Wasserstein distance, and Wasserstein distance is somehow related to the IPM, and maybe you can compare this to approach somehow. I'm not pretty sure, but I think it's quite nice. So if there's any question, I'm all available. Thank you so much for your attention.
Okay, thank you. Thanks for the nice presentation and questions. I'll stop recording now.